April 21, 1943, 11:20 a.m., Jebel Jaffa, Tunisia. The German Tiger tank numbered 131 sat motionless at the base of a wadi, its massive 56-ton bulk tilted at a 15-degree angle. The crew had abandoned it 3 hours earlier after American artillery fire damaged the engine compartment and jammed the turret traverse mechanism. Before fleeing, they attempted to destroy it with demolition charges, but the explosives only partially detonated, leaving the vehicle damaged but largely intact. Captain Philip Corso of the United States Army Ordnance Department stood before the Tiger with a mixture of reverence and disbelief. This was the tank that had terrorized Allied forces across North Africa, the armored monster, whose 88mm gun could destroy any Allied tank at ranges exceeding 2,000 yards, whose frontal armor was impervious to every weapon in the American arsenal. And now it belonged to the United States Army. What Corso didn't know, what nobody in the Allied command structure could have predicted, was that American mechanics were about to do something the German engineers who designed this tank would have considered impossible. They would completely rebuild this Tiger tank, correct its fundamental design flaws, and make it mechanically superior to any Tiger rolling off German production lines. The story of how American ingenuity transformed Germany's most feared weapon into a reliable fighting machine would change Allied understanding of German technical capabilities and reveal that superior engineering didn't always mean superior design. Sometimes it meant knowing when to choose simplicity over sophistication, reliability over performance, and practical solutions over theoretical perfection. This is the story of Tiger 131, the German tank that American mechanics captured and rebuilt better than the Germans ever could. The Tiger tank represented the pinnacle of German armored vehicle design when it entered service in August 1942. Officially designated Panzerkampfwagen VI Tiger Ausführung E, it was conceived in response to encounters with heavily armored Soviet tanks on the Eastern Front. German designers created a vehicle intended to dominate any opponent through overwhelming firepower and invulnerable protection. The specifications were impressive by any standard. Weight, 56 metric tons. Armor, 100 mm. Frontal plate, 80 mm side armor. Main armament, the legendary 88mm KK-36 gun derived from the Flak 18 anti-aircraft weapon. Engine Maybach, HL, 230P, 45V, 12, producing 700 horsepower. Maximum speed 23 miles per hour on roads, 12 miles per hour cross-country. But beneath these impressive specifications lay engineering decisions that prioritized performance over reliability, complexity over maintainability, and theoretical perfection over practical durability. These decisions would prove catastrophic in extended combat operations and would provide American mechanics with opportunities to demonstrate superior practical engineering. The capture of Tiger 131 occurred during the final phase of the Tunisian campaign, when German and Italian forces were compressed into an increasingly small perimeter. The 2nd Battalion, 69th Armor Regiment, encountered the abandoned Tiger on April 21 near Jebel Jaffa after its crew fled under American artillery fire. Lieutenant James Buckley, commanding the recovery team, later described the initial assessment. "We approached carefully because we'd been told Tigers were booby-trapped after abandonment. This one had scorch marks and blast damage, clearly from attempted demolition, but the hull was intact and the turret, while jammed, wasn't destroyed. We realized immediately this was an intelligence goldmine." The recovery operation took 3 days. American engineers used 2 M4 Sherman tanks and 4 M3 half-tracks to tow the 56-ton Tiger 12 miles to the Ordnance Department's field depot near Beja. During transport, the Tiger's transmission failed completely, its final drive units seized, and its suspension began losing road wheels. The Germans' most advanced tank was falling apart simply from being moved. Captain Corso's initial examination revealed the extent of the damage. The Maybach engine had taken shrapnel through the cooling system and showed evidence of severe overheating. The turret traverse mechanism was jammed due to damaged gearing. The transmission was completely destroyed. Multiple road wheels and suspension arms were broken. The final drive units had failed catastrophically, but Corso recognized something more significant than battle damage. He saw fundamental design weaknesses that made the Tiger mechanically fragile despite its combat superiority. The transmission, a Maybach Olvar Type OG 4001-2-8, incorporated 8 forward gears and 4 reverse gears in a semi-automatic design of extraordinary complexity. It contained over 2,000 individual parts, required precise adjustment, and could not tolerate any contamination or wear. The final drive units, which transmitted power from the transmission to the drive sprockets, were engineering marvels of compact design. They incorporated a reduction gear system so precisely machined that tolerances were measured in hundredths of millimeters. This precision made them efficient but catastrophically fragile. Field mechanics called them glass gears because they shattered when subjected to shock loads. The suspension system, featuring interleaved road wheels designed to distribute the Tiger's massive weight, was a maintenance nightmare. Each road wheel was 40 centimeters in diameter and weighed over 200 pounds. The interleaved design meant that changing an inner road wheel required removing multiple outer wheels first, a process taking up to 10 hours in field conditions. In winter, mud and snow froze between wheels, completely immobilizing the vehicle until thawed. Major John Milliken, commanding the Ordnance Department's Armored Vehicle Testing Section in North Africa, made the decision that would transform Allied understanding of German armor. Instead of simply studying the captured Tiger, they would completely rebuild it using American maintenance practices and see if they could make it actually work reliably. The project was unprecedented. No Allied nation had successfully restored a Tiger to operational condition. The British had captured Tigers in Tunisia, but shipped them to England for static examination. The Soviets had captured several Tigers on the Eastern Front, but lacked the specialized tools and knowledge to make them operational. American mechanics would attempt something more ambitious. They would rebuild Tiger 131 not to German specifications, but to American standards of reliability and maintainability. If successful, they would demonstrate that American practical engineering could overcome German theoretical sophistication. The rebuild began in early May 1943 at the Ordnance Depot near Beja. The team consisted of 12 mechanics from various American armored units, supervised by Captain Corso and Master Sergeant Thomas Mitchell, a pre-war automotive engineer from Detroit who had worked for Chrysler. The first challenge was the transmission. The Maybach Olvar was completely destroyed beyond any possibility of repair. Even if parts had been available, which they weren't, the transmission's complexity meant only factory-trained specialists could rebuild it. American mechanics would need to improvise. Sergeant Mitchell examined the transmission mounting points and driveshaft connections. He realized that while the Tiger's transmission was German, the basic mechanical principles were universal. Power needed to flow from engine to drive sprockets through some form of gearing that provided speed reduction and directional control. The solution was audacious. Mitchell proposed installing a transmission from an M4A3E8 Sherman tank, modified to mate with the Tiger's drivetrain. The Sherman transmission, a Spicer manual synchromesh unit, was vastly simpler than the German Maybach. It had only 5 forward gears and 1 reverse, contained fewer than 800 parts, and could be completely rebuilt by competent mechanics with basic tools in under 6 hours. The engineering challenges were substantial. The Sherman transmission produced different output shaft speeds and rotational characteristics than the Maybach. The mounting points didn't align. The drive shafts were different diameters. The cooling requirements differed. But American mechanics possessed something German engineers typically lacked: extensive experience with improvised repairs and field modifications. They had spent months keeping Shermans, half-tracks, trucks, and tank destroyers running under combat conditions with whatever materials were available. Adapting a Sherman transmission to a Tiger was simply another field modification, albeit an unusually ambitious one. The modification took 18 days. Mechanics fabricated adapter plates from salvaged armor steel, machined new driveshaft couplings on improvised lathes, and created custom motor mounts using welding techniques. The result was mechanically crude compared to the original German engineering, but it worked. Initial testing revealed problems. The Sherman transmission's gear ratios weren't optimized for the Tiger's weight, resulting in poor acceleration and reduced top speed. But reliability was extraordinary compared to the original Maybach. The simplified gearing tolerated abuse, contamination, and wear that would have destroyed the German transmission within hours. If you're fascinated by these incredible stories of World War II innovation and engineering, please subscribe to our channel and hit that notification bell. We bring you the untold stories of how ordinary people achieved extraordinary things through creativity and determination. The final drive units presented the next major challenge. These precision-engineered components had failed catastrophically and were beyond repair. The German design, while efficient, could not withstand the shock loads generated by combat maneuvering or rough terrain. Sergeant Mitchell's solution was to abandon precision in favor of durability. Using gears salvaged from destroyed American tank destroyers and half-tracks, mechanics fabricated crude but robust final drive units. The American replacements were heavier, less efficient, and generated more heat than the German originals, but they were virtually indestructible under normal operating conditions. The gear teeth were cut with broader profiles and deeper roots, sacrificing efficiency for strength. The housings were fabricated from thicker steel, adding weight but providing massive structural rigidity. Lubrication systems were simplified, eliminating complex oil pumps in favor of splash lubrication that was less efficient but far more reliable. The resulting final drives reduced the Tiger's top speed by approximately 3 miles per hour and decreased fuel efficiency by 10%, but they could withstand operating conditions that would have shattered the German originals within hours. The suspension system modifications were equally pragmatic. The interleaved road wheels, while distributing weight effectively, were a maintenance disaster. American mechanics couldn't eliminate the interleaving without complete redesign, but they could modify the system to improve reliability. Each road wheel was removed, inspected, and rebuilt. Worn bearings were replaced with American equivalents that, while not precisely matching German specifications, provided adequate performance with vastly improved availability. The complex German bearing seals, which failed frequently and required specialized tools to replace, were replaced with simpler American seals that could be changed with basic wrenches. The torsion bar suspension, which provided excellent ride quality, was retained but reinforced. Mechanics welded reinforcing plates to mounting points that showed stress cracking, sacrificing weight efficiency for structural integrity. Most significantly, they modified the interleaved wheel arrangement itself. By adding removable access panels to the hull sides, they reduced the time required to change inner road wheels from 10 hours to approximately 3 hours. This modification, accomplished with cutting torches and welding equipment, demonstrated practical problem-solving that German engineers, constrained by factory production requirements, had never considered. The engine presented fewer challenges than expected. The Maybach HL230P45 was damaged but repairable. American mechanics, after examining the V12 engine design, recognized it as fundamentally similar to American radial aircraft engines in operating principles, if not specific configuration. Shrapnel damage to the cooling system was repaired using techniques developed for field repair of Sherman engines. Damaged coolant passages were welded and pressure tested. The cooling fan, which had suffered blade damage, was rebuilt using hand-formed aluminum sheet. Electrical systems were rewired using American wire and connectors that, while not matching German specifications, provided equivalent functionality with improved reliability. The fuel system received particular attention. The Tiger's fuel pumps, which operated at high pressures to ensure adequate fuel delivery, were prone to vapor lock and cavitation. American mechanics modified the system using fuel pump designs from Wright radial engines, reducing operating pressure but improving reliability. The trade-off was slightly reduced power output at maximum engine speed, but significantly improved starting and idle characteristics. By late June 1943, Tiger 131 was mechanically complete. The rebuilt tank bore little resemblance to German factory specifications. The transmission was American. The final drives were improvised hybrids. The suspension incorporated dozens of non-standard modifications. The engine ran on American fuel and lubricants using American electrical components. On June 28, 1943, with Captain Corso commanding from the turret and Sergeant Mitchell driving, Tiger 131 started successfully and moved under its own power for the first time since capture. The rebuilt tank completed a 2-mile test course that included rough terrain, steep grades, and high-speed runs on improved roads. The performance data revealed the impact of American modifications. Maximum speed was reduced from 23 miles per hour to approximately 19 miles per hour. Acceleration was noticeably slower. Fuel consumption increased by approximately 15%. The transmission shifted roughly compared to the original German semi-automatic system, but reliability was extraordinary. Over the following 6 weeks, American mechanics drove Tiger 131 for over 200 miles during testing and demonstrations. The tank operated continuously for up to 8 hours daily. It completed obstacle courses that subjected it to severe mechanical stress. It was deliberately driven through conditions designed to break mechanical components. The Sherman transmission never failed. The improvised final drives showed no signs of stress. The modified suspension performed flawlessly. The rebuilt engine ran smoothly on American gasoline that was lower octane than specified for German engines. By contrast, German Tigers operating in Tunisia during the same period showed catastrophic mechanical failure rates. German maintenance records captured after the Tunisian surrender revealed that Tiger tanks averaged 25 miles between mechanical breakdowns. Transmission failures were endemic. Final drive failures occurred so frequently that spare units were carried on recovery vehicles. Suspension breakdowns immobilized tanks regularly. The reasons for German unreliability became clear through examination of Tiger 131 and interrogation of captured German tank crews and mechanic. German engineering had pursued theoretical perfection at the expense of practical reliability. The Maybach transmission, with its 8 forward speeds and semi-automatic shifting, provided theoretically optimal power delivery across all speed ranges, but this sophistication required maintenance that was impossible under field conditions. The transmission required oil changes every 60 miles. Adjustment procedures required specialized tools and factory-trained technicians. Any contamination or wear caused immediate failure. The final drives, designed for maximum efficiency, operated with minimal safety margins. The precisely machined gears could not tolerate shock loads, overloading, or any operation outside narrow parameters. German maintenance manuals specified that final drives should be replaced after 150 miles of operation, a maintenance interval that was impossible to meet in combat. The interleaved suspension distributed weight effectively but trapped mud, snow, and debris. In winter conditions on the Eastern Front, Tigers frequently froze solid overnight as accumulated material between road wheels turned to ice. Crews had to light fires under tanks to thaw them before movement was possible. American mechanics, examining these design decisions, recognized a fundamental difference in engineering philosophy. German engineers had designed the Tiger for theoretical maximum performance, assuming that maintenance would be performed under ideal conditions by trained specialists using proper tools and genuine parts. American engineers designed vehicles for reality. They assumed that maintenance would be performed under terrible conditions by exhausted mechanics using improvised tools and whatever parts were available. They prioritized reliability over performance, simplicity over sophistication, and maintainability over theoretical perfection. The rebuilt Tiger 131 embodied American engineering philosophy applied to German hardware. It was slower, less efficient, and mechanically cruder than factory specification Tigers, but it worked reliably under conditions that would have destroyed German-built Tigers within days. Major Milliken's final report on Tiger 131, submitted to Army Ground Forces Headquarters in August 1943, contained findings that would influence American tank development for the remainder of the war. The Tiger tank possesses superior firepower and armor protection compared to American medium tanks. However, German engineering has produced a vehicle of extraordinary mechanical fragility. The Tiger's sophisticated systems cannot be maintained under field conditions and fail catastrophically when operated outside narrow parameters. American mechanics successfully rebuilt the captured Tiger to operational condition using improvised components and field modification techniques. The rebuilt tank demonstrated reliability far exceeding German-manufactured vehicles, despite reduced performance. This demonstrates that American practical engineering and maintenance capabilities represent decisive advantages over German theoretical sophistication. The implications were significant. American tank designers, who had been pressured to match German technical specifications, received validation that their approach, emphasizing reliability and maintainability, was correct. The Sherman tank, frequently criticized for inferior performance compared to German armor, was vindicated as a superior practical design for sustained combat operations. Tiger 131's operational career continued beyond initial testing. The tank was used extensively for training American tank destroyers and infantry in anti-tank tactics. Crews could practice engaging an actual Tiger tank, learning its silhouette, vulnerabilities, and capabilities. During these training exercises, weaknesses in the Tiger's design became apparent that weren't obvious from technical examination. The turret, while heavily armored, traversed slowly, requiring 60 seconds for a complete 360-degree rotation. American tank destroyers learned they could exploit this by rapid maneuver, forcing the Tiger to continuously traverse while lighter American vehicles engaged from multiple angles. The Tiger's gun, while devastating, had limited depression, preventing the tank from firing at close targets on steep slopes. American infantry learned to exploit this by approaching through terrain that negated the gun's range advantage. Most significantly, training revealed that the Tiger's mechanical complexity made it vulnerable to mobility kills. American tank destroyer crews were taught to target the drive sprockets, road wheels, and engine compartment. Even non-penetrating hits on these areas could cause mechanical failures that immobilized the tank, making it vulnerable to subsequent attack. The British received detailed reports on Tiger 131's rebuild and requested access to American maintenance techniques. British tank crews, facing Tigers in Italy and later in France, benefited from knowledge that German mechanical reliability was poor and that aggressive tactics could force Tigers into situations where their mechanical fragility became a liability. Soviet forces, informed through intelligence channels about American success rebuilding Tiger 131, began implementing similar approaches with captured German armor. Soviet mechanics, already experienced in improvised repairs under terrible conditions, proved adept at keeping captured German vehicles operational, using crude but effective modifications similar to American techniques. The psychological impact on German forces of learning that Americans had successfully rebuilt a Tiger tank should not be underestimated. German propaganda had portrayed American engineering as inferior, American mechanics as incompetent, and American military technology as crude and unsophisticated. Oberst Hans von Luck, commanding armored forces in North Africa and later in Europe, wrote in his post-war memoir about the impact of reports that Americans were operating a captured Tiger. "We had believed our Tigers were too sophisticated for American mechanics to understand, much less repair. When we learned they had not only repaired one but improved its reliability, this was profoundly disturbing. It suggested that perhaps American practical engineering was superior to our theoretical perfection." By September 1943, Tiger 131 had logged over 500 miles of operation without mechanical failure. This exceeded the operational life of most German Tigers, which typically suffered transmission or final drive failure within 250 miles. The tank was eventually shipped to Aberdeen Proving Ground in Maryland for detailed technical examination. Engineers from Army Ordnance, representatives from American tank manufacturers, and liaison officers from Allied nations spent months examining every aspect of the rebuilt Tiger. The technical reports produced from this examination influenced Allied tank development significantly. The T-26 heavy tank program, which would eventually produce the M-26 Pershing, incorporated lessons learned from Tiger 131. American designers understood that heavy armor and powerful guns were valuable only if the vehicle could be maintained under combat conditions. The Pershing featured a powerful 90mm gun and heavy armor comparable to the Tiger, but with mechanical systems emphasizing reliability and maintainability. The transmission was a Torquematic automatic unit designed for simplicity and durability. The engine was a Ford Gaff Vate producing 500 horsepower, using components from proven American automotive applications. The suspension used torsion bars similar to the Tiger but without interleaved wheels, dramatically improving maintainability. If you've enjoyed discovering how American ingenuity transformed Germany's most feared weapon, please subscribe and hit the notification bell. We share these remarkable untold stories of World War II innovation and the creative problem-solving that changed history. German tank designers, receiving intelligence reports about American modifications to Tiger 131, initially dismissed American approaches as crude and unsophisticated. But as the war continued and Tiger mechanical failure rates remained catastrophic, some German engineers began questioning their design philosophy. Ferdinand Porsche, designer of the Tiger P and later the Tiger II, acknowledged in captured documents from 1944 that perhaps excessive sophistication had been a mistake. A report to Albert Speer noted, "American armor demonstrates that adequate performance with high reliability defeats superior performance with poor reliability. Our Tigers achieve theoretical superiority, but practical inferiority." This recognition came too late to influence German production. The Tiger II, introduced in early 1944, incorporated an even more complex transmission than the original Tiger, even more precisely machined final drives, and interleaved suspension with even tighter wheel spacing. Mechanical failure rates were worse than the original Tiger, with some units reporting that fewer than 50% of Tiger IIs were operational at any given time. By contrast, American tank production continued emphasizing reliability. The M4 Sherman, despite acknowledged inferiority in armor and firepower compared to German heavy tanks, maintained operational readiness rates exceeding 85% throughout the war. American armored divisions could count on their tanks working when needed, while German panzer divisions struggled with mechanical failures that rendered theoretically superior vehicles useless. The final disposition of Tiger 131 came in 1946 when the tank was transferred to the United States Army Ordnance Museum at Aberdeen Proving Ground. It remained on display there until 1976, when it was transferred to the Patton Museum of Cavalry and Armor at Fort Knox, Kentucky. In 1995, the tank was loaned to the newly established National Armor and Cavalry Museum at Fort Benning, Georgia, where it remains today. The Tiger still contains many of the American modifications installed in 1943, including the Sherman transmission, improvised final drives, and modified suspension components. Museum placards describe it as the only Tiger tank captured and completely rebuilt by American forces during World War II, but the deeper story of what that rebuild represented receives less emphasis. Tiger 131 stands as testament to the triumph of practical engineering over theoretical sophistication, of maintainability over performance, and of American ingenuity over German precision. Captain Philip Corso, who supervised the initial capture and rebuild, continued serving in armor development throughout the war and into the post-war period. He retired as a colonel in 1955 and worked as a consultant for American defense contractors. In a 1978 interview, he reflected on the Tiger rebuild project. "We learned that German engineering, for all its sophistication, had fundamental flaws. They designed for perfection rather than reality. They assumed ideal conditions rather than planning for terrible ones. American mechanics, working with basic tools in field conditions, rebuilt that Tiger better than German factory workers could have. Not faster or more powerful, but more reliable, more maintainable, more practical." That said, everything about why we would win the war. Master Sergeant Thomas Mitchell, the Detroit automotive engineer who designed many of the key modifications, returned to civilian life in 1945. He worked for General Motors until retirement in 1972. He rarely discussed his wartime service, but colleagues reported that he kept detailed engineering drawings of the Tiger modifications he had designed. Those drawings, preserved in his personal papers donated to the Smithsonian Institution, remain a masterclass in practical problem-solving under resource constraints. The broader lesson of Tiger 131's story extends beyond World War II into fundamental questions about engineering philosophy and design priorities. When designing complex systems, should engineers pursue theoretical maximum performance or practical reliability? Should they assume ideal operating conditions or plan for worst-case scenarios? Should they design for trained specialists or for average operators? German engineering culture, rooted in precision manufacturing and theoretical optimization, consistently chose performance over reliability, sophistication over simplicity, and specialization over generalization. This approach produced remarkable achievements in peacetime but proved catastrophic in war, when sophisticated systems had to operate under terrible conditions with minimal maintenance. American engineering culture, rooted in mass production and practical problem-solving, consistently chose reliability over maximum performance, simplicity over sophistication, and maintainability over theoretical perfection. This approach produced systems that often appeared crude compared to German equivalents, but proved vastly more effective in sustained combat operations. The Tiger tank, Germany's most feared armored vehicle, embodied the strengths and fatal weaknesses of German engineering. Its 88mm gun could destroy any Allied tank at extraordinary ranges. Its armor was impervious to most Allied weapons. Its sophisticated systems provided theoretical performance advantages over any Allied equivalent. But it broke down constantly. It required maintenance impossible to perform under combat conditions. Its complex systems failed when operated by exhausted crews under stress. Its precision components couldn't tolerate the contamination, abuse, and improvised repairs that characterized actual combat. American mechanics, examining this technological marvel, recognized that sophistication without reliability was worse than useless because it created dependency on systems that would inevitably fail. Their rebuild of Tiger 131, substituting crude but reliable American components for sophisticated but fragile German systems, demonstrated that sometimes the best engineering solution is the simplest one that actually works. Modern military vehicle development continues learning from Tiger 131's lessons. The United States military emphasizes reliability, maintainability, and sustainability as primary design requirements alongside performance. Vehicles are designed assuming they will be maintained by soldiers with basic training using common tools under terrible conditions. Sophisticated systems are incorporated only when they provide decisive advantages that justify increased maintenance requirements. The M1 Abrams main battle tank, America's current primary armored vehicle, embodies this philosophy. Its turbine engine provides exceptional power and performance, but was chosen primarily because it can operate on multiple fuel types and requires minimal maintenance. Its suspension system provides excellent mobility but was designed for rapid replacement of components using basic tools. Its fire control systems are sophisticated but designed for reliability under combat conditions. German military vehicle development, influenced by lessons learned during World War II, abandoned the pursuit of theoretical perfection in favor of practical reliability. The Leopard 1 and Leopard 2 main battle tanks, Germany's post-war armored vehicles, emphasize maintainability and reliability alongside performance. German engineers learned that practical durability defeats theoretical sophistication. The story of Tiger 131 continues resonating because it illustrates a fundamental truth about technology and engineering. Sophisticated systems that don't work reliably are inferior to simple systems that work consistently. Theoretical performance advantages mean nothing if systems fail under actual operating conditions. And sometimes the best solution is not the most elegant one, but the crudest one that actually functions when needed. American mechanics who rebuilt Tiger 131 in 1943 understood these truths intuitively. They weren't concerned with theoretical perfection or sophisticated engineering. They focused on making the tank work reliably using whatever materials and techniques were available. Their success demonstrated that practical creativity often matters more than theoretical knowledge, that field experience often beats academic training, and that sometimes the best engineer is the mechanic who can make things work with whatever tools are available. The 12 American mechanics who transformed a broken German superweapon into a reliable fighting vehicle exemplified democratic ingenuity at its finest. They weren't specially trained Tiger experts. They didn't have factory documentation or specialized tools. They simply applied practical problem-solving skills developed through years of keeping vehicles running under terrible conditions. Their achievement stands alongside the more celebrated technological triumphs of World War II. While scientists developed radar and proximity fuses and nuclear weapons, ordinary mechanics armed with wrenches and welding torches demonstrated that American practical engineering could overcome German theoretical sophistication. They proved that sometimes the greatest innovations come not from laboratories but from workshops, not from blueprints but from improvisation, and not from following specifications but from ignoring them in favor of what actually works. Tiger 131, sitting in its museum display at Fort Benning, tells this story to visitors who understand its deeper significance. The tank looks like any other Tiger to casual observers, but careful examination reveals the crude American modifications that made it work better than German factory originals. The Sherman transmission, where a Maybach should be. The improvised final drives built from salvaged parts. The modified suspension with its American bearings and seals. Each modification represents a moment when American mechanics looked at German sophistication and said, "We can do this better, simpler, and more reliably." They were right, and in being right, they demonstrated a truth that Germany's theoretical engineers never fully grasped, that in warfare, as in life, adequate performance maintained consistently defeats superior performance achieved rarely. That reliability matters more than sophistication, that systems must be designed for reality rather than theory, and that sometimes the best engineering solution is the simplest one executed competently rather than the most complex one executed perfectly. American mechanics captured a Tiger tank in April 1943. By June, they had rebuilt it better than German engineers ever could. Not faster, not more powerful, but more reliable, more practical, and more useful. In doing so, they demonstrated why America would win the war through engineering superiority that had nothing to do with theoretical perfection and everything to do with practical competence. That lesson, embodied in a 56-ton German tank rebuilt with American improvisation, remains as relevant today as it was 80 years ago. Tiger 131 stands as monument to the truth that sometimes the best solution is not the most sophisticated one, but the simplest one that actually works when you need it to.